Here we are in week 5 of social network analysis. This week we're going to be looking at small world networks. The concepts this week are going to be combining what we learned about random graphs, in particular Erdős-Rényi random graphs. What we found interesting about those is that those can really grow. You can get networks of millions of nodes, and yet the average shortest path, which scales just as the logarithm of the number of nodes, will then be, something on the order of 10. And that seems quite remarkable. Then we looked at some real-world networks and discovered that they had interesting community structure. That is, on a somewhat more localized scale, the structure is not random, but we haven't yet really delved into the very local structure, the structure of the network around a particular node. So what we're going to be doing this week is filling the gap. Is it possible for real-world networks to have small world properties like random networks do, and at the same time, can we recognize the interesting structure they have at the local, level? So just to outline, I'm going to start with Milgram's famous small world experiment, which established that it's a small world when you look at social networks. Then I'm going to be looking at some local structure and metrics, starting with the clustering coefficient and then delving into motif analysis. I'm going to then present some models, the very famous small world model by Watts and Strogatz that reconciles networks having clustering and at the same time having short path lengths. And then we're going to look at a few other small world models having to do with geography or having to do with hierarchical groups. And finally, we're going to look at not just take these small world networks for granted, but say, where does this structure arise from? Why do we get small world networks? And then next week, we'll be looking at some of the consequences. What does small world structure mean for diffusion, for learning, and for coordination? So, that's still to come. Okay, on to Milgram. Stanley Milgram was a Harvard sociologist who wanted to know how many hops is it between any two individuals in the United States. So he recruited, I think he put an ad in the newspaper, individuals in Nebraska and actually in Massachusetts as well, but the Nebraskans are the more interesting set. And he gave them a task. He said, here's this stockbroker in Massachusetts. I want you to mail this pamphlet to him, but you can't do it directly. You can't just, stick it in the mail. You're supposed to mail it to someone that whom you know on a first name basis. And they're going to mail it to someone who they know on a first name basis. And we're going to see how many steps it's going to take. Back then, when he asked people how many steps they thought it would take, most of them guessed hundreds because they were thinking of their local network. Most of the people they knew were rather local. And so Massachusetts seemed awfully far away, and they just imagined it would take lots and lots of steps. That turned out to not be the case at all. The average number of steps was 6.5, and this is how the expression 6 degrees of separation was coined. This experiment was repeated in 2003 with email. And the task was very similar, but you had 18 targets instead of one target, 13 different countries, and you had far larger initial participation. So they got 60,000 participants into the experiment, 24,000 message chains, but only fewer than 400 actually made it to the target, versus Milgram had about a 20% completion rate. And here, the average shortest path, which spanned the globe, was really short. It was just 4 steps. So let's think about whether 6 or 4, we'll see how 4 is not the right number, really, how you can correct for it. Whether that's surprising. So in order to figure that out, first we need to know on average how many individuals does someone have in their network. Pohl and Cohen in 1978 did a study and estimated that the number's around 500 to 1,500 acquaintances. So let's be conservative and let's say it's 500. And let's also imagine that we're in a random network. And so your friends are just randomly chosen. So they're very unlikely to overlap with your friends. Now, if everyone has 500 friends, the average person would have how many friends of friends? Okay, so if you have 500 friends and each of them has 500 friends in turn, you would expect 250,000 friends of friends. Pretty neat, right? As long as the network is random. Now, let's extend this to friends of friends of friends. Okay, in this case, we have 500 to the third power, and that it means that, once you're 3 hops out, you have 125 million friends of friends of friends, and that starts to resemble a significant portion of the US population. So the conclusion is that if networks are random, then 6 is not a surprising number at all. In fact, maybe it's a little bit on the large side. What if, on the other hand, networks were completely cliquish, right? So all of my friends' friends are my friends as well. They're not allowed to have any other friends outside of my friends. Well, in that case, what would be true? So in that case, you actually can't reach any other part of the network because you're in a complete clique and no one's allowed to have any edges outside of that clique. So you're distance 1 to anyone within the clique, but you can't reach, it's like infinite distance to anywhere else. So now the question is, this small world phenomenon, how does it arise, right? It seems very natural in a random graph, but in an entirely cliquish graph, we're not sure whether it can arise. But first, let's talk about the accuracy of the number 6 or 4, depending on which experiment you're talking about. One reason why this isn't necessarily an accurate number is that not all the chains are completed. And the question is, are shorter chains more likely to be completed than longer ones? And one consideration is, what is the attrition rate? And also, is that attrition rate uniform with respect to, whether that person is the next one in the chain from the starting person? They might approach it with greater enthusiasm because they were recruited. So the initial person was recruited, they might be interested, they might they might write the next person and say, this is such a cool experiment, try it out. But then that person may be passing on with less enthusiasm. Similarly, maybe the people further down in the chain are actually getting closer to target, so maybe they're less likely to drop the message because the goal might be near. However, neither of those turns out to be true. You have pretty stable attrition no matter which step in the chain you are. So now we can start to calculate the probability that a message gets through given a constant attrition rate. So let's say it's half probability that someone's going to pass the message versus just not do anything with it. And so if you have a chain of length 2, so 1, 2, you have only this person's in question, right? The initial sender sends for sure, otherwise there's no chain and we don't count it. And the recipient receives it, so they don't have to take any further action. So here, we're just wondering, is this person going to pass it on? So let's calculate the probability that a chain of length 2 gets through, and then a chain of length 5. So you should see that a chain of length 2 is much more likely to pass through than a chain of length 5. And so you can then go back and try and infer what the true distance distribution is. So for example, for the email experiment, their average number of hops was 4, but once they corrected and said, well, the longer chains were less likely to get through, they had an estimate of a median chain length somewhere between 5 and 7, sort of recovering that 6 degrees of separation again. A second factor in how accurate that number is that individuals actually may not be finding the shortest paths. Right? So they don't know the global structure of the network. All they're doing is they're passing the message onto someone they think is more likely to know the target. And there was this nice study in 2005 that mapped out completely a network within an organization. So they had that map. And then they had those individuals, so the map was who talks to whom, right? And then they ran Milgram's experiment, which said, pass this to someone that you normally talk to. And they saw that roughly half the time, the individuals routing the message chose the next node to be on the shortest path, and half the time they goofed in a way. They didn't choose the shortest path. So even for the successful chains, they may not actually lie on the shortest path. So 6 might be an overestimate. Now, recently there was a study done at Facebook showing that any 2 Facebook users are 4.7 hops apart. And the question is, what does that really mean? If you look at these different social networking services like Facebook, like Twitter, like LinkedIn, and I would definitely recommend listening to the interview with LinkedIn because this question is addressed in there, or Google Plus, what direct and indirect benefit do you get from someone who's 1 hop away, 2 hops, 3 hops, etc.? So just something for you to think about.